All right, guys, we are the group boss Freddy. Okay. Can I start?
Yeah, just wait for yeah, start.
All right, guys, we are the group boss Freddy. So our project is predicting housing sales price in M's lower. This is our team introduction. So if you are watching this video, please contact us if your company is looking for data science or data analytics talents. My name is Cheng, and this is my teammate Paul Dingus, Wenjun and Haoyun Zhang. All right, and this is the data exploration part. The purpose of this project is to predict the housing price with least error, which is RMSE, root mean square error, by using over 80 input variables, which are the information about the houses, including over quality, above grade, living area, neighborhood, and so on and so forth. So basically, we trained 5 models based on those variables, which are proven to be effective, including Lasso, ridge elastic regression, and gradient boosting, XGBoosting, and finally we use the stack regressor to combine them together to get better performance. And that's it. All right, so exploring our data set is usually the foundation of our following procedure and modeling. So we took a look at the distributions of our variables and the relationship between input and output variables. From the distribution of our variables, we found that some variables are significantly skewed that might need to be standardized after following steps. And from relationship between X and Y, we found like outliers exist and some variables have strong linear relationship with price. Noticing that this is our output variable, which is the sale price, and this looks like obviously like right skewed. So we would like to take a look at it like specifically. Here it is. So we can see that there is a violation of normality assumption of linear regression that manifests in the target feature that is notably right skewed. And what we want to do is like to transform it by taking the log for the sake of the model fitting in the last step. And we also found like there are many outliers in our data exploration. So we filter out those outliers in important features that have high correlation with sales price, and we remove them. But there are so many outliers in different variables, so we decided just to select the important features which are like having high correlation with our output variables, and we filter them out as what I circled here, and we move them, and you see it seems like pretty tidy and ready to get into the next step. All right, so this is missing value. Welcome my teammate Wenjun.
Okay, so after dealt with those skewness things, we dealt with the missing values. So as we can see, there are a lot of NANs in our data set. If we count everything in total, there are about like 14,000 missing values in both train and test data set. In the train data set, there is 6,965, and in the test data set, there is 7,000 NANs. And in the training data set, there are 19 features with missing values. And in the test data set, there are 33 features with missing values. But fortunately, not all these NANs are missing. For example, in the training data set, some features like alley, pool, QC, those NANs are caused by no alley access, no pool, no fence, no fireplace, no garage. So it's easy to deal with those kind of NANs. We just need to impute those NANs by no something. And there are some missing values, such like basement and frontage and MAS VNR type, and the area, and 1 electrical. So for the basement, as we can see on the left-hand side, there are 37 of basement quality, condition, and finish type 1 finish type 1. But for like finish type 2 and exposure, there are 38. That means some NANs are caused by real missing, not just no basement. So for those kind of houses, I group them by neighborhood and year build, try to figure out the most popular way of build and the house. So I decided to impute those values by the mode. And for lot frontage, I still dealt within the neighborhood, and I selected the median as the imputation of the missing value. And for MAS VNR type and MAS VNR area, still I checked the neighborhood and the close year build, and I selected the mode as the imputation. And for electrical, I checked all the years after that house is built. I think it's probably because of some regulation. All the electrical type is SBRKR, so I imputed this one with SBRKR. And in the test data set, I did not list those NANs because of no basement, no garage, no fireplace, no pool stuff. I only listed those ones which do have missing values. So for the basement part, I noticed that ID 2218, 2219, and 2349, they have some wrong inputs, because they are supposed to have no basement, but they do have some inputs for other features of the basement. So I had no way to figure out what's going on here, so I decided to delete the information of basement and count them as missing values. And same for the garage, ID 2127 and ID 2577. They have wrong inputs, so I deleted the information of garage and treated them as missing values. And the lot frontage and maybe I should smaller this size. It's a little weird. So
when you transfer it to PowerPoint.
Okay. Never mind. So let me see. So the lot frontage, I did the same thing as in the training data set, and MAS VNR type and MAS VNR area. Some of them are because of there is no MAS VNR, and I think there is one or two. I selected the most popular thing for the year and neighborhood as the imputation, and because MAS VNR area has one less missing values, so these are seriously just no this kind of decoration, so I impute that with 0. And for MS zoning, I still group by neighborhood and selected the most popular values for those 4 NANs to impute. And utilities, still, I think almost all of them are all pub, so I imputed that with all pub. And the exterior one is also the most popular for the year build and neighborhood. And for kitchen quality and functional, there apparently should be something there, but I just had no idea how to impute those, so I just eyeball the quality of other features and impute TA and mod. Those are kind of average quality. And the cell type, the most common one is WD, so I imputed that one for WD. And so after imputation, we're ready for feature engineering.
Thank you very much. So feature engineering is the stage of the process where we have no missing values. We've dealt with outliers and deleted them, and we're ready to get our features prepared for our modeling. So as everybody probably knows, with this data set, there's a huge amount of non-numeric data. So that presents the biggest challenge. Going about it the correct way, or in a very careful way, actually yielded a lot of improvements for us in our score. This is something that we came back and iterated on quite a number of times. So the first thing I want to talk about is the different types of variables that you'll encounter here. The first is the easiest variable to deal with, which is just continuous. So this is anything like area, square footage, lot frontage. And all we needed to do for those was just ensure that they were numeric, that it wasn't coming in as a string. But then in terms of the non-numeric data, there was ordinal categorical and nominal categorical, which should be treated differently. For ordinal, we manually constructed encoders to apply values to these based off of their relative respective ranking. So in the middle box there, you can just see a brief example of one of the more sort of common ordinal value sets that you might see, and how we encoded it into an ordered numeric value set. And here's some examples of the ordinal variables that we encoded. And in terms of nominal categorical, where there's no clear order to the data, we went about dumbifying them, which was not a simple process, and I'm going to talk about that on the next few slides. This is an example of a non-ordered categorical data type, heating down here. And when we looked at the box plots of these, it was clear that a good number of the categories in each of these variables were not numerous enough or different enough to be effective. So you've got to remember that when you're dumbifying data, each of the categories in the respective, or in the variable of concern creates a new column. So this is a really a dimensionally intensive process. If you just dumbify everything, you'll end up with over 100 additional columns. And we wanted to prevent this, especially with these categories that aren't going to provide much valuable information. And so when we saw something like this in heating, where there are several categories that have extremely few variables or extremely few observations and are quite similar in their values, we wanted to group them so that we didn't overflow our data set with variables. Here's a graphic explanation of how we went about doing this. For the variables you'll see on the left there, and then in this middle section, you'll see the different categories that we grouped together, and then the resulting name that we gave to those categories. And this ensures that once we go about dumbifying, that the columns that we end up with are going to be providing valuable information for our modeling. And I think what we found is that most of the columns that we created in this process were canceled out through our regression processes anyways, through Lasso. And the second thing I want to talk about, and Freddie mentioned this earlier, is the skewness of some of our variables. If you look at just the histograms of a lot of the variables, you'll notice very quickly that a lot of them are skewed left or right. We wanted to make sure that we improved this aspect of some of our input variables before we went out modeling. And we went through a pretty simple log transformation process where if the skew was above a certain threshold, we would apply a transformation. Then I think we applied it up to 2 times if the skew was still above a certain threshold. And at the bottom here, I mentioned that there are a few extremely skewed variables that we spotted and manually applied power transformations to. And as you can see on this slide, it did create a respectable improvement in the amount of skew that we saw in our input variables. So on the left there is the skew of some of our more skewed variables before this transformation process, and on the right is afterwards. And you can see that especially with some of the more extremely skewed ones, this process did help us out a little bit, and we also did see an improvement in scores through this process. So that is the end of our feature engineering section, and it's also the end of our sort of data exploration and cleaning process. And I just want to reiterate what a lot of teams have said, is that we discovered that this had more impact on our score than any of our modeling improvements ever did. There's only so much you can do with modeling and in optimization in that portion. And feature engineering did turn out to be extremely important for us. And throughout the project, we went back and improved this aspect of our project a lot, which helped with our scores. So I'm going to hand it off to Haoyun to talk about modeling.
Hi everyone, I'm Haoyun. So last step is to model fitting. So the first part we did is the Lasso regression. We want to use this regression to select our features. So we did this plot like the RMSE with lambda, and to see like different lambdas how much RMSE decreased or increased. So we can see like here in this point, like the life of this point, the RMSE was decreased. It means like if we consider this all features, we will create the overfitting. But like the right side, if we reduce this, like remove these features, we will create like some underfitting. So we based on this plot and to like find the optimal optimized lambda to select all of these features, and based on this figure, well, it's hard to see which one is becomes to 0 first. So we create a data frame to point out all features which, like different lambda, which feature will come, the coefficient goes into the 0, which means it's not that important when we choose the lambda as that point. So the total number of feature dropped is 119. Well, it's a lot. Okay, so next we compared like before the feature selection and after feature selection. We can see our RMSE was decreased a little bit, and it's as we can see here, after we doing the feature selection, the model here seems like more flattened. It's like our feature selection, like I think it's doing well, and like there's a slightly change about this. RMSE, and like our lambda, we will choose to like optimize as this number as our Lasso regression. So also we use the same method to do this ridge regression, and we want to see how much like our RMSE can change or decrease or increase after we doing the feature selection. So we can see this. From the Z1 0.11. to draw into the 0.1091. So it has some decrease of our RMSE. So I think like after feature selection, our model will become more fitting for our ridge. So and then we do these three basic models, and to see like after we dropping our feature and how our RMSE and R squared changed. So compare with these three models, for our elastic, I found like when we choose the row as 1, it means like only the Lasso regression it will have the great result. But however, the elastic regression still have the lower like RMSE compared to the Lasso regression. So the first step we choose the Lasso regression as our model to like predict our feature price. So here's the first score we got from the Lasso regression. So after we learn the XGBoosting and the extreme gradient boosting, we try the other two models. And we want to try these 5 models together using stack regressors to like create our new data set to improve our prediction. So for gradient boosting, there's 2 parameters we optimize the what's that called? The first one is the number of the estimators, and also the what's that? The rate of the the rate of the learning rate of this regressor. So this is the whole picture of the score we can get. The XGBoosting, we didn't use the grid search to optimize our parameters because our computers are not that good to do this stuff. So we just changed the parameters like manually to get this data, this score. But I think we can do it better in the future if we can, if our computer allowed us to do that. So after the stacking and to select which regression has their own percentage, we can get a pretty good result as our like final stack RMSE. And when we submit our score, we can get like 0.1168 as our like Kaggle score. So that's the whole thing of our project. So yeah. Any questions?
Okay, so, oh wow, right on time too. On my end, toward the end of the day, so hopefully I can collect all my thoughts properly. I felt the presentation overall was very well laid out. Also, certainly, it looks like if you guys didn't prep the presentation, then even more well done because it felt very prepped also in terms of how you went through the humble right there. In terms of how you guys kind of went along with the steps, like who was going to say what, and then also the process as a whole. The part, I do feel there was part of it where when you were discussing missingness and also feature selection, part of that, I was missing a bit of the why and the rationale behind what your findings were, or rather what the conclusion of your findings were from that process. I felt a lot more of it was talking about like what you guys were doing rather than like what came from it. Like what, like for example, once you imputed, like did you observe any difference in results where the feature is used, valuable? Same thing with the feature selection. I like the fact that you observe the challenge of what happened to the same categorical feature that had say like 10 to 12 different categories, and say you got like 20, 30 of them. You're looking at 300 extra variables, and if you choose to like just simply do a doublification or whatnot, which obviously is not was not the way you want to handle it. So it's good that you observed it, but I couldn't quite I didn't know what came after. So that's just something to take note of in terms of the presentation itself. I also got a little lost towards the model selection part. Maybe it's because I just didn't hear correctly or whatnot, but I actually didn't quite know what happened towards basically after this slide. Like I kind of got lost in the presentation part. So I'm not going to ask you to repeat it, but for the sake of time, but maybe somebody else could chime in. But for example, I couldn't quite understand what you meant by when you hit XGBoost. I think I heard you manually check the hyperparameters.
Yes.
And I didn't know what that meant actually, because XGBoost, I don't even know how can you manually check the hyperparameters.
Just change the parameter to see what results is better, or it goes better or like worse. Like change some numbers of its parameters.
Like literally, you just test the random values.
Well,
Okay.
not one like I searched some on like which number like is good to use like an estimator. So they use like if we use the more than one solvent or.
Oh, as in like you did some rule of thumb.
Yes,
and
roughly
okay.
to change it.
Okay, I understand. Okay,
Yeah.
all right. Yeah, because that.
It's not like
I didn't.
really.
Yeah, I was gonna say. You definitely don't want to end up going into a situation where you're like, yeah, I'm using
Yeah, my
radio
computer.
boosting method, and I just manually tweak the parameters.
Yeah.
That probably will, raise a few concerns.
Sorry, now that we're in this page, which kind of feature selection you mean here? So before feature selection, what was that? The feature selection that you showed here? Feature selection. What was that?
I use the Lasso regression to see like whether we need to like
think that's
Cool.
Yeah, well done.
Thank you.
Thank you. Thank you.
Happy birthday, Paul.
Happy birthday.
Okay, so it might take me a bit. I'm gonna have some like kind of common aggregated feedback also I'm gonna type up and then Slack it as a whole in terms of just what I observed across the board. But yeah, nice job.